My name is William Kirchu, and I'm just going to be showcasing my assignment number 5. So the first thing I did was the cost functions, and as you can see here, the quadratic cost was actually implemented for us already, so we don't have to worry about that. Cross entropy, we just have to deal with the derivative, which is just a minus y divided by a times 1 minus a, where a is the network output, y is the target output. Log likelihood, we only care when where the target out where y equals 1 rather. Um, and the formula is negative natural log of the network output where y equals 1 at that index. And we do np.nan in case we get a nan value here. And for the derivative, similar deal, except the formula is negative 1 over the network output where y equals 1. Otherwise, we set it to 0 and we return that column vector. So if you notice, the values returned for the functions is scalar, and the derivatives is a column vector. Next, we have to do the activation functions. So sigmoid was already provided for us. Softmax, we already got the derivative, so we just have to do the function. And this is the formula. It just involves Euler's number and applying it to each value in the column vector. So it's just Euler's number to the power of z, and then dividing by the sum across Euler's number to the power of each of those values. That's the formula. I got it from the PDF, and it's implemented correctly here. For tanh, for the function, this is the formula. NumPy actually has a tanh function call that I could have used, but I just wanted to write out the whole formula, and here it is. Derivative is just 1 minus, the function applied to z squared. And Rayleigh is pretty straightforward. You just take the the vector and just return basically all negative values in the vector become 0. Otherwise, the positive values stay the same. And similarly for the derivative, if the values are greater than 0, just make the values 1. Otherwise, they're 0. So those are the cost and activation functions. With respect to the difference between hidden and output activations, so for output, one thing that was noted is that the tanh only works with quadratic cost. So I had to, if I ever use tanh with a cost that's not quadratic, I change it here. So self.cost equals quadratic. This is the error message. It only accepts quadratic costs. And I applied the same thing in set parameters as well. That's the exact same thing. As for applying the functions to the hidden and output layers, you just gotta adjust for that in the feed forward phases. So feed forward function here for BW and self.biases, basically all the way up to the output layer. So this is only the hidden layers. We apply the appropriate activation function to the hidden layers. And this is just the activation function for the output layer, the final layer. So that's how I accounted for that in the feed forward function. And it's the same thing in back propagation. Just down here, you do your stuff and on the hidden layer in this for loop. This is the hidden layer. And then you just apply the same thing to the output layer here. Activation equals self. So that's that. The next thing we had to deal with was regularization and update mini batch and then total cost. I'm just going to go through this real quick. So where's update mini batch? Right here. So if self.regularization equals L1, we apply that L1 regularization formula in updating the weights, similar with L2 here. Otherwise, we just do W minus delta W when there's no regularization. And then we have to account for the regularization as well in total cost in the evaluation phase. So this is the formula for that. So if regularization equals L1, you apply this formula. And this was provided by the professor. I saw on Piazza that we had to put a 1 here for L1 regularization in this linear algebra normalization function call. And for L2 regularization, it's just that function call squared on the weights. So that's that for regularization. And now I believe it's dropouts, which is probably the more challenging part, but I think I got it. We have to create a dropout mask for each mini batch. So I create a dropout and an empty list called dropout here at the start of updating a mini batch. And when we call the backpropagation function, I actually added a new parameter here called dropout, and we're just passing in this list in there, and I'll show you how that's dealt with. So dropout, so we have new mask equals 0, and if not dropout or the dropout is empty, then we set new mask equals to 1. And the feed forward phase, we do if dropout percent greater than 0 and new mask equals 1. So if that list is empty, basically, we need a new mask for the hidden layer. We create the random binomial to be applied to the activation. So basically, it's going to take out some nodes for us depending on the percent we put in there. And then we append that vector, I guess, to dropout. So that's going to be our mask. And this is the 423 data set, so there's going to be one hidden layer. So it's only going to be one mask there. And then again, if self.dropout percent greater than 0, we apply that to the activation function. And because the dropouts only apply to hidden layers, we do not do the same thing to the output layer here. So you won't see the dropout over here. And I'll just note that I'm returning the dropout list, so to speak. You know, that binomial. So it's just going to keep cycling in. And now I'm just going to quickly showcase like how the code runs. I'm just going to run all here. So it's quick because I only have a few seconds here. And these are my results. This is the error for the training, and then the accuracy, error for test and accuracy. So it's a similar setup as the what the professor gave. And yeah, if you just look through these, you'll find that it matches all the results. So all these combinations match. Anyways, that's pretty much all I have to showcase for you. Thank you for your time.